Next property is the convolution theorem. Suppose f of t and g of t are two functions defined in an interval 0 infinity with the Laplace transforms capital F of s and capital G of s. Then Laplace transform of convolution of f of s, convolution of f and g is given by L of f star g equal to capital F of x into capital G of s. That is Laplace transform of convolution of f and g equal to product of their Laplace transform. The convolution product of two functions f of t and g of t is defined by integral 0 to t f of u g of t minus u du. The another version of the convolution theorem is L inverse of capital F of s into capital G of s equal to f of t star g of t. Now we have another function called unit step function. Unit step function is defined by u of t minus a equal to 0 if t is less than a, u of t minus a equal to 1 if t is greater than a, for all a greater than or equal to 0. Laplace transform of u of t minus a is given by the integration, and finally we get it is e raised to minus as divided by s for s greater than 0. In particular, Laplace transform of u of t equal to 1 by s, that is L inverse of 1 by s equal to u of t. Another important function is unit impulse function or Dirac delta function. The function is defined by delta of t minus a equal to infinity when t equal to a and equal to 0 when t not equal to a. This function has a property that integral 0 to infinity delta of t minus a dt equal to 1. With this definition, its Laplace transform is given by L of delta of t minus a equal to e raised to minus as. Therefore, Laplace transform of delta t equal to 1, which implies L inverse of 1 equal to delta t. Second shifting property, that is, if L of f of t equal to capital F of s, then L of f of t minus a into u of t minus a equal to e raised to minus as into capital F of s. That is, f of t minus a into u of t minus a equal to L inverse of e raised to minus as into capital F of s. This property is called the second shifting property. One of the important applications of Laplace transforms is the solution of linear differential equation using transforms. The method of solution of linear differential equation using Laplace transforms. The first step is take Laplace transform on both sides of the given differential equation and apply the given initial conditions. This gives an algebraic equation in y bar, where y bar is the Laplace transform of y of t. Step 2. Solve the algebraic equation to get y bar in terms of s. Step 3. Take the inverse Laplace transform of y bar that gives y as a function of t, which is the solution. We can use property 4 for taking Laplace transform of derivatives.